Hello, this is a quick and dirty information session on the Bohr model of an atom. Based on the Bohr model of an atom, now before I get too far into this, remember the only two elements that really look like this are hydrogen and helium. But we'll talk a little bit about that next week. But for now, electrons are assigned to certain levels, but the word they really like is orbits. So think of this as different orbits or circles. Electrons can move from one level or orbit to another, but cannot be between levels. You have to go all the way or stay with the one you're at. A blank of energy is needed to change levels. A jump, increase. Let's use the word increase. Or I'm going to write underneath this, decrease. So an increase or decrease of energy is needed to change levels. What we're going to be looking at is a decrease in just a minute, and we'll see that through light. But first, we'll look at a Bohr atom. If you look boron atom, like me, boron. So you remember we got our first orbit. We have 2 electrons. Second one, we would have 1, 2, 3. And I was looking on a periodic table when I was counting those. So according to the Bohr atom, Bohr model, that's what boron would look like. What about oxygen? So again, got your nucleus in the center, 2 electrons on the first orbit, and on the second orbit you would have 6. And someone might say, how did you get that? You put your finger on the periodic table and you find oxygen. So I count backwards. 1, 2, 3, 4, 5, 6. So that's where I got those 6 electrons for that. I'll let you try magnesium on your own. Okay, going to flip this. Flip it how? Flip it real good. So Schrödinger did a mathematical modern description of of electrons in an atom. So we have what we call the probability model. And this is based on, like I said, probability. Does not involve electrons staying in an orbit around the nucleus. This shows a probability that's somewhere in here. Remember the example of Mr. Key being somewhere in the room, but you don't know where? All right, so here we're going to go back to the Bohr model. When an atom becomes excited, the electrons gain energy and move to an excited state. When electrons fall back to the ground state and energy is released in the form of photons or light. You also can see that in colors. We use the Bohr model for a hydrogen atom. There you go. To determine the wavelength that's released. You're not going to believe how easy this is. So let's look down at the bottom. So here we go. When you see n equals, as soon as you ever see n equals on a test, I want you to grab this chart. Looking at this chart a little closer, notice that all the arrowheads go which direction? Inward. So all of these are falling back to the ground state. If you ever see an answer choice of going from like 1 outward to 2, 3, or 4, you know that's not the answer. Because none of these have arrows going out. They're all going in. Okay? That's very important. And we're going to be using these numbers down here to help us find the answer. So which of the following photon transfer will result in the largest wavelength? These are all measured in wavelength, so it's just the largest number is all that's saying. All right? So let's find the largest number. From 4 to 1, watch what I do here. N equals 4, and I come around to the dot of n equals 1. And that number is 97. So that answer is 97. Is that the biggest? I don't know yet. 3 to 2. 3 to 1, that's not right. 3 to 2 is right here, and that's 656. Feel free to stop that if you don't see where that's 656 nanometers. Don't like naked numbers, do we? Okay. 2 to 4 is what? Wrong. Can't have that one. It's going out. Can't happen. 6 to 3, 6. Come around. 6 to 2, 6 to 3. 1094. 1094. Which number is biggest? 1094. Well, that was pretty easy. Let's try another one. This one we're looking for the highest energy. Energy is the same as frequency. So when those go up, wavelength goes down. Remember that earlier? That's inversely proportionate. So here, what number are we looking for with the highest energy will be the lowest wavelength or number. So let's see. 3 to 1. 3 to 1. Second number of 103. 3 to 2 we've already done. And of course these are in nanometers. 1 to 4, bad choice. And 6 to 3 is 1094. Now, unlike the last one, we're looking for the lowest number because it's the highest wavelength would be the lowest. Sorry, the highest energy would be the lowest wavelength. Highest energy, lowest wavelength. So the lowest number here is A. All right. Which of the following will result in the lowest frequency? So we're looking for the lowest frequency, which would be the highest wavelength. So just the highest number. Okay? This always helps me. It tells me which one I'm looking for. 4 to 1, we've already done, 97. 3 to 2, we've already done, 656. 4 to 2, not an option. 4 to 3, we haven't looked that up yet. So let's look that up. 4, come around. That's 4 to 1. 4 to 2. So 4 to 3 is way over here, 1875. So we're looking for the highest number, and that is by far the highest number. All right, let's flip the page. Oh, that's it. Be aware that sometimes we ask questions about is the number in the infrared spectrum, visible spectrum, or UV spectrum. Remember, it has to be in the visible spectrum. You would come down here and find a color. Now let's talk about that for a second. The three colors up here are 656 nanometers, which would be somewhere in here, in the red range. 650 would be right there. This is 700. You may want to write this on your chart. This is 590, 570, 490, 420, and 400. These are in nanometers, whereas the numbers with times 10 to the 7th are in meters. All right? You see up here, meters, and of course the numbers up here, nanometers. So they're trying to trick you there. But if you wrote this in, you'll never miss one of those. All right? I hope this helped. Please look through your sheet, and hopefully you'll be able to answer all the questions. Have a good week.